Hello, and thank you for joining us for the next session of the Destination IP Virtual Summit. In this session, Sabine Folkmer-Ward, Jose Nunez, and Garth Vivier will discuss writing patent applications for machine learning and AI-related technologies. A recording of the webinar and the slides will be made available to all registrants. Feel free to enter any questions using the Q&A feature in the Zoom menu. Also, feel free to follow us on LinkedIn to see news about other upcoming webinars. Sabine Folkmer-Ward's practice focuses on patent prosecution and portfolio development across a wide range of technologies and industries, both software and hardware related. Sabine has extensive experience in the patenting of software inventions, including complex algorithms, and in particular, AI/ML related inventions. Sabine completed her undergraduate studies in physics in Germany and obtained a graduate degree in physics from MIT. While a graduate student at MIT, Sabine competed in a student-run entrepreneurship competition and co-founded a startup company in the internet search space. This exposure to the intersection of technology and business is what sparked her interest in patent law. Sabine obtained her JD from Suffolk University Law School in Boston. Jose Nunez is a patent attorney with over 13 years of experience. His practice focuses on computer software and hardware, machine learning, networking, semiconductor manufacturing, network storage, and security. Before practicing patent law, Jose was a network engineer and product manager for Hewlett-Packard, Sun Microsystems, and Trimble Navigation. Jose has developed in-depth experience in machine learning, making multiple presentations on the subject of patenting AI, and writing articles for IP Watchdog, including how to help data scientists overcome their patent doubts and the long reach of the mathematics patentability exception is overbroad and absurd. Jose obtained a degree in telecommunication engineering from the University of Madrid. He also has a Master of Science in Computer Science and a Master in Business Administration from Santa Clara University. Jose obtained his JD from Northwestern California University in Sacramento, California. Garth Vivier is a registered patent attorney and principal of Schwegman, Lundberg, and Worcester. Garth is included in Intellectual Asset Magazine's IM 1000 listing of distinguished patent attorneys. His focus for 28 years has been on the procurement of high-value patents for both multinational corporations and startups. On a regular basis, Garth assists startups in Silicon Valley and abroad to develop IP strategies tailored to the tight budgets most startups face. A patent strategy should be closely aligned with business objectives, and he has gained practical insight into how to accomplish this. Garth, Sabine, and Jose were actively involved in preparing comments responsive to the USPTO's request for comments on patenting artificial intelligence inventions. And with that, I'll hand things over to Sabine, Jose, and Garth.
Thank you, Michelle, for the introductions, and thank you for those folks online joining us today. We look forward to doing this presentation, and hopefully you'll find it useful and informative. Just a high-level outline of what we'll be talking about today. AI patenting, then we'll move on to the machine learning framework, considerations for drafting patent prosecution, then some examples of machine learning stroke AI patents. And then we'll finish off with the best practices. Next slide, please, Michelle. So many of you looking at this image will think we're now going to talk about facial recognition and so on. But the image you're seeing, these people are not real. There's a website called This Person Does Not Exist. And this is from that website. The website uses, well, the underlying technology was developed by Vivier. And it uses a technique called generative adversarial networks, also known as GANs. And with GANs, there are two networks, the generator and the discriminator. The generator synthesizes new examples, new faces from scratch, and the discriminator takes samples from both the training data and the generator's output. And it makes images, creates these images of people which are not real. If you go, next slide, please, onto the website, This Person Does Not Exist, you'll see each time you load the website, in a fraction of a second, a new face is generated. So it's absolutely fascinating where ML/AI, and maybe I'll just refer to ML, is applied these days. There's been an explosion of interest in the ML AI tech space in the last few years. And I think the view is that ML/AI patenting is a subset of software-related patents. There are some very specific guidelines which we provide in writing these applications, because they do require some additional information that normal software-related invention applications would not require. There's almost daily articles on new applications of AI and even funding of AI of startups. This week there were numerous, if you read the tech blogs and websites, you'll see there were numerous funding publications or announcements this week, several $7 million in many to many of these machine learning AI startups. The AI is such a diverse technology. You know, it's being applied from self-driving cars to medical applications, for example, customized drugs. And earlier this week, you know, the COVID-19 is obviously very topical at the moment, but Harvard Global Health Institute and Google released a COVID-19 public forecast app, which is actually a set of models providing projections of COVID-19 cases utilizing ICU information, providing ICU utilization, ventilator availability, and other metrics over the next 14 days. Other applications which are in our daily lives would be voice recognition, digital assistants, etc. I think probably one of the most insightful articles I've read recently was an article on TensorFlow. As many of you may know, TensorFlow is actually Google's software framework for creating AI programs. And the framework has been around for about 5 years and been downloaded 100 million times to date. And what's even more astounding is that it was downloaded 10 million times in May alone. So clearly, you know, there's been a tremendous growth in this tech space. Next slide, please. I don't plan on dwelling on these slides very long, but just to, this will give you just an idea of the business value of AI. A $2.9 trillion business value is expected in 2021. Next, please. Of interest here would be AI patents by geography, and you'll see the US still leads the field, but I know that China have a focus on AI patents, and it wouldn't surprise me if the number of applications there rise significantly, as in with the other countries. Next, please. Just give you an idea, the hockey stick or exponential growth of AI patent applications at the USPTO. Now, we could discuss the business side of things for quite some time, but I don't think that's the focus of this discussion. So I'd like to now hand over to Jose and ask him to give us an overview. What is AI? Jose?
Yeah, thank you, Garth. Yeah, basically the typical or the old-fashioned definition of artificial intelligence is the use of machines to mimic cognitive functions associated with humans, such as learning and problem solving. And however, I think this definition might be a little antiquated. Let me give you an example. In July 2019, an inventor named Dabus, D-A-B-U-S, filed 2 applications in the US and Europe named Food Container and Devices and Methods for Attracting Enhanced Attention. DABUS stands for Device for the Autonomous Bootstrapping of Unified Sentience. And the last name is, open quote, invention generated by artificial intelligence. A project from, well, close quotes, a project from the University of Surrey for a swarm of many disconnected neural nets. Of course, in a few months, the EP and the USPTO came out and said, sorry, the inventor cannot be a machine. And like in the US, they address talks about the code talks about individuals or whoever invents. So machines cannot be inventors. But we know that artificial intelligence can do things that humans cannot do. They can analyze large amounts of data. They can extract correlations. So I think a better definition would be learning and problem solving by non-living entities. That is what artificial intelligence. Now, with artificial intelligence, the law is developing as accordingly. For example, some issues are what happens if AI bot provides legal advice? Is that okay? What happens if the advice is wrong? What happens if my self-driving car goes down a cliff? I mean, what is the liability? Is the car manufacturer, the guy that did the algorithm, the guy that did the training data? And so there's questions about how the liability for AI. Also, elimination of bias. What if artificial intelligence makes a decision to hire somebody based on the person profile? What if all of a sudden start finding the best candidates are the ones in better neighborhoods because they have better education? So there's initiatives, and some of the states already put out laws to eliminate bias from artificial intelligence decisions, and there's technologies to do so. And what about patent prosecution? As you might know, the US Patent Office is looking at artificial intelligence to improve their searching capabilities. So they're good at, the benefit of artificial intelligence is can analyze context, so the searches can be much more focused. So we can see a future where examination is taking place by an AI bot. And what if the patent office allowed that application, that bot to two practitioners? Maybe we can have an application that might have been developed by an AI bot and run it right away and see what the examination would be. And then maybe we can get a new model that would provide an amendment, etc. So you can see how the prosecution could go from years to maybe hours. So, but that's the future. We're not there yet. So another issue is that where are AI patents going? There's these questions from the patent office, NEP, all the different jurisdictions are looking at how to handle AI. And our belief is that AI will follow the same path as software. Software, maybe 20, 30 years ago, there was a panic how we're going to look at all these software inventions. But it will turn out to be the same way in patent. Just because you put something in a program that is obvious or doesn't have novelty doesn't make it patentable. So AI will follow the same thing. You're going to have to let some technical details, some technical implementation, some novelty, utility to make AI patents patentable. Another issue that comes up is some people are skeptical about machine learning patents, especially you talk to data scientists. Data scientists think everything is obvious. So everybody's saying, oh, everybody's using the same tool, so where's the novelty? Or, well, if you do this, the model, there's no detectability or there's no transparency. How are you going to detect if somebody's infringing? But it's not always true. I mean, I think it has a value of patenting your technology. Imagine you're making widgets and you have a main competitor that make widgets too. And you use machine learning to find a better way to make widgets. Imagine your competitor hires the data scientist. He goes to the other side and implements exactly the same solution. So you're gonna wanna have two to have a patent to stop him from doing that. And you always, you don't want to be in the end and trying to show, going to litigation, that that those patents are not valuable. It's better to be the ones that have the patents in their pocket. Anyway, so with that, I'm gonna ask Sabine to give us a little bit more detail about machine learning, because these days AI, even though there's different algorithms, how to do it in the old way, there was expert systems or scoring systems, but today AI is driven by machine learning. So Sabine, can you please give us some information about machine learning?
Yes, of course. Thank you, Jose, for this high-level introduction of artificial intelligence. Michelle, can we go to the next slide, please? I'd like to provide a bit of an overview over the machine learning framework. So as Jose said, we are going to focus on that. And I will stick with his understanding of artificial intelligence or machine learning specifically as learning and problem solving by a non-living entity. And so the points I'm going to address is to talk a little bit about the models, the machine learning models themselves that perform these tasks, and then the algorithms that are used to build and train the models. And in that context, I'd like to point out some aspects of machine learning that are patentable. Garth mentioned, or Michelle mentioned up front, that we were involved in providing comments to the USPTO last year, was in response to a request for comments on AI issues. And one of the questions asked was, what about AI or what about machine learning is patentable? Now, the short answer, I would say, is everything. But we will give some illustrations also further down in the talk and in the examples of what aspects might be patentable. Next slide, please. So what is learning? Well, I would offer that learning means acquiring the ability to perform a certain task based on observation and experience. Now, in the case of a machine with a computer, the observation and experience always take the form of data. And any kind of raw input that you might get, an image, text, an audio signal, other kind of sensor data, any type of information is ultimately converted into some kind of mathematical object or data structure. And we often refer to this in the context of machine learning as input features. So we extract from the raw data kind of the elements that might be relevant in ultimately predicting an output. The task that's being learned, that the computer learns to perform, is essentially a program that's ultimately executed. So a program that takes an input and provides some output. And just to give some examples of such tasks that both the machine and the human might perform, something simple for a human but hard for a computer is, for example, facial recognition, right? So we learn this as infants. It boils down to a classification task based on some images. You determine whether some person is Mike or Bob. Another task that takes us as humans a little bit longer to learn, usually years, is reading, which essentially is text-to-speech conversion. And the computer similarly can take an input sequence of text and, for example, turn it into an audio signal. And the inverse is, of course, also true. Speech recognition. It's another example of a sequence-to-sequence conversion task. Or as yet another example, we might learn to drive at some point in our life, and a computer similarly in a self-driving car, for example, can learn to drive and make decisions, in this case, the output or control signals, based on some kind of sensory input. Or as one last example, imagine you're trained as a physician, you're diagnosing illnesses based on symptoms that you observe in patients and that they tell you about. Well, a computer similarly might take a set of pieces of input information, the input features, and come up with a diagnosis, another kind of classification task. Or it could be a probabilistic, this is the chance that you have such and such condition. Now, what makes machine learning is that the program that converts the inputs to the output is not given explicitly. Rather, it is constructed, at least in part, by the computer from the data. So in a way, the computer programs itself. And I think that's what gives us the sense of artificial intelligence. Now, in learning from the data, the computer develops a model of the data. It extracts the essence of the data, if you will. And then it uses that model to make the predictions for new input data. That I think is an important point and key distinction from mere data analytics. Machine learning does not just involve developing the model, but it's really a predictive model. So if you learn from a set of images, for example, the computer learns to distinguish between Mike and Bob, later on a new image it has never seen before can be provided as input and can result in the same kind of classification. This is Mike or this is Bob, based on that model. To be specific, let me give you a few examples of the types of models that we're talking about. Now on the left, I'm depicting a very simple regression. That's one of the most simplest examples you can think of. Here in this case, we have one input feature X and one output feature output element Y. Think, for example, of a parent of a newborn. We might want to know whether the child is on track in growth, and so X might be the age of the child and Y may be the weight. So a simple correlation. The model that captures this kind of correlation is depicted here as a red line, or you could describe it as a mathematical equation, y equals mx plus n. And so this is really the machine learning model, very simple case. And it's a fit to the data. The blue dots are the input from which the model is derived. As another example, go back to the example of a physician making a diagnosis. Now the physician might ask, if you are wondering whether you have allergies, for example, what your symptoms are. Do you experience itching or nasal congestion? Do you have a temperature? Are your symptoms seasonal? So this is a kind of binary question that in a binary decision tree could result in a classification, a binary classification in this case, whether you have allergies or not. And as you can see at the nodes of this decision tree, or the non-leaf nodes, the branching points, the input features corresponding to the individual symptoms are used here. Now, a decision tree can be obviously more complex. It can have, it need not be binary. It could also be a regression tree that gives you kind of on a continuum, a number as the output, as opposed to just a classification. One more example is that of a neural network. And neural networks have gotten a lot of attention over recent years, and there's been really a wealth of research going on in this area. In a neural network, the data structure mimics, in a way, the connections in our brain. And so we talk about neurons. These are these circles here that take in a number of input features. Again, on the left, you see x1 through x3. And then on the right, it produces some output. I have here a two-dimensional output. It could be one-dimensional, it could be many dimensions. So say, for example, the input is an image, the features of the image, and maybe the output is a probability distribution over, say, what kind of animals you're seeing. Or the input could be a sequence, a character sequence, and you use optical character recognition to determine an image sequence, and you determine what the characters are in the abstract. So in this neural network, at the nodes, the input signals are combined so that the nodes generate a linear combination, typically followed up by some kind of nonlinear function that's applied. And each of these individual columns of nodes that you can see here could mathematically be represented as a matrix. So that's kind of the data structure. Now in deep learning, which is what we nowadays mostly talk about in the context of neural networks, you simply have multiple of such layers, and it can get rather complicated. So this just to provide an overview of the models. Now in the next slide, we go into the machine learning algorithms. So what does the algorithm do? How does it actually build the model from the data? So you see some training data, that's what we refer to, the data that's used to generate the model. Well, typically you start with some specification of the general structure of the model. Do you have a decision tree, or are you looking for a function of some kind? Or are you using a neural network or any of a variety of other machine learning models that exist? And oftentimes these, you start with a model that has certain parameters that are adjustable. For example, in the neural network context, the elements of the matrix that describe the individual layers of the network are also referred to as weights. They can be adjustable. So they're initialized at the beginning of the training process, but then iteratively they are refined based on some kind of feedback, and I'll get to that in a moment. In the case of a regression, the model with the adjustable parameters might be the equation that you're starting out with, a linear equation, a quadratic equation, a polynomial, exponential, what have you. And the parameters there are adjustable. So you can, for example, change, or the machine can change the slope of the line that you're drawing to better fit the data. Let me talk about, just for a moment, about the, I think, most familiar machine learning paradigm, which is supervised learning. In supervised learning, the training data includes pairs of an input and a corresponding output. And the learning algorithm, which is a program performing the training, right, the building of the model, it takes that input, feeds it through the machine learning model, which generates an output. And then that output is compared against the output that was part of the training data. So you have a label, you get the image of Bob with the label, this is Bob. The image is fed to the model, it makes a guess, this is Bob or Mike or whoever. And then the output is compared, and you use an objective function to determine kind of the difference between the two. And that difference can be used to be fed back into the model. Now, in many cases, you have these adjustable parameters. In some cases, it's really hard to distinguish between the model and the learning algorithm. And oftentimes, these two terms are conflated. And in some cases, I think that's somewhat justified. For decision tree, for example, the model is kind of programmed into the learning algorithm. I think implicitly, you start building the decision tree from scratch. Now, these different types of models have their own associated training algorithms. So they come kind of in pairs, if you will, though some general algorithms might be applicable to different models. And similarly, a particular model may have different algorithms associated with it that could be used for training. But I've listed just some examples here, starting at the bottom with neural networks. The typical type of algorithm that's used is backpropagation of errors, where you're using this objective function to determine the difference between the output generated by the model and the label in supervised learning. And you use that error and go backwards the network to adjust the weights. In a decision tree, you might start with the data and partition it in a recursive way to kind of find the discriminative features that give you an answer of the output if it's a classification task. And so a greedy algorithm might be used for that. In regression, it could be a simple kind of least squares optimization. So you're trying to get the best fit to the data points that you have. Now, you might be skeptical and say, well, is this all machine learning, a simple regression task, or in some cases, a simple decision tree? Maybe you wouldn't call this machine learning, maybe you wouldn't call it artificial intelligence, but I think it does fit in the general framework. And what it comes down to in the end, in my view, is really a matter of degree. If it's a more complex task, if the machine does more of the adjustments and there is less explicit structure put in the model in the first place, I think it goes farther in the direction of artificial intelligence. Let me just, next slide, please, just throw in a couple more things. So when talking about what aspects of machine learning are patentable, all of these boxes that you see here, I think could be patentable. So the model in and of itself could be an aspect of a patent. You might use a known algorithm, say for a neural network, the backpropagation of errors to train a model, but maybe there's a particular structure, certain constraints that you impose. The matrix of an individual layer might not be, entirely free. It could be a sparse matrix, maybe in diagonal form or something like that. So these kinds of decisions go into the model, which a human typically specifies. And so that could be an element of a patent. Or maybe the model is fixed, but you're using a learning algorithm that does the adjustments of parameters faster. That could be an invention. Or in some cases, you have a model, a known model, and a known learning algorithm, but the objective function is tweaked in some way. For example, in a non-supervised learning context, you might derive some general statistics of data and then compare the output of your machine learning model against these statistics, let's say an entropy type function, a cost function of some kind, and measure how close it is. How well does the generated data match the statistics? So machine learning model, the learning algorithm, the objective function, along with the model, the input features might be relevant. So there might be some pre-processing of the raw input to even get to input features suitable as input into the model. And then the training data, that might be an element. And then what you see here in active learning, for example, you could have a tool that allows a human to interact with a machine and the machine to request, for example, more samples of labeled input data to perform the training. Next slide, please. And yet another example is...
Sabine, while you're talking about that, you have the different models and you mentioned different components are all patentable. Could you just briefly, even though we're going to get to claiming later, discuss the issue about when you do draft claims for these type of inventions, do you explicitly include the training or implicitly include the training of the model, to avoid divided infringement problems? Could you just briefly address that, and we'll discuss it in more detail later?
Yes, it's exactly the kind of question I'm asking myself when drafting patent claims, whether to include it or not. And it always depends on where the gist of the invention lies and what the client's goal is, what kind of product you want to cover. So, for example, if you're thinking of an end user application, say an app you download onto your cell phone that takes images and does something with it, maybe I don't know, generates a collage or something like this, or recognizes faces and then gives you some kind of output. Now, in that case, what you want to patent, what you want to potentially enforce against an infringer is the functionality of that trained model. And I don't want to have the training algorithm in the claim, ideally. Now, if the training algorithm is important for the point of novelty, I might try to get at it with some kind of implicit claiming, where I'm saying, for example, a machine learning model trained by performing such and such steps, and so that's almost like a product by process type claiming. But in some instances, the training algorithm is really where the invention lies, and it might be provided say as software as a service by a client, a company, to others to use to build their own machine learning models. And in that case, of course, you could craft the claim directing it to the learning algorithm itself. So it always depends, but it's a really valid consideration as to what you want to achieve and where the gist of the invention is. And so that last point actually ties into the case of auto machine learning, where you have software software, a program that selects and configures the learning algorithm, a second program, to then generate a third program, the machine learning model. So it can get quite complicated. If we can move on to the next slide. We're going now into some kind of general practice considerations, and I will talk a little bit about understanding the invention, describing it, claiming it, so kind of the front end of the patent process. And Jose will give his input later and maybe focus on prosecution obstacles he encountered and how to address them, so kind of the back end of prosecution. Next slide. Understanding the invention. Well, a good starting point, of course, when you're getting into any kind of field is to get some background. And there are ways to learn about machine learning. There are plenty of resources available. If you wish, you could start even with a college level course. There are lots available on Coursera, for example. But it's also, I would say, possible to learn on the job. And whatever you do, I think regardless of how much you prepare to get into the area, there'll always be some learning on the job needed in the end, simply because it's such a sprawling field and such an active area of research. To give you an example, I once got an invention disclosure, which was 15 pages long, excellent, very detailed. And on page 11 in the middle, it had a subtitle, Invention. And so the description of the invention didn't start until page 11. In this case, the first 10 pages were background, and it was excellent. There was nothing superfluous there. It just takes a while to get to the point in some instances because it's such a young area of research. So oftentimes when I get an invention disclosure, say from a an academically inclined inventor who has a publication draft, and maybe that triggers the need for patent filing. I look at that draft and say it's an invention from 2020. It might reference back or build on inventions from 2019, 2018. Now that's far past the time when I left graduate school, right? So it's not something where I can just build on my general education, but I have to kind of work up to that point. And that is, I think, one of the distinguishing features as a practical matter of a lot of these AI ML inventions. In a lot of other areas of my practice, I don't encounter that quite as much. There's also always, of course, the point of novelty that I have to understand in an invention, but what it builds on, say in hardware, often the physics principles, the underlying ones, are the same as existed 20 years ago. In machine learning, I find more often than not, in the complex algorithmic cases, that it takes a long time before I get even to the point. And I'm stressing this point because in drafting an application, it's important to really get there and not, not end up at a layer that's just not deep enough. So sometimes I think you have to go down the rabbit hole to get there. And it's really important to identify where exactly the invention resides, because that will also steer your efforts in what to focus on. What I found very useful in practice in understanding an invention is, as I mentioned, the academic articles that the inventors sometimes provide. Even if I have, say, a transferred in patent application that I'm prosecuting and I'm reading the specification, I've gotten into the habit of asking whether there is a corresponding academic publication, because it's just written in a different way, often getting to the point quickly. The inventors spell out the contributions of these papers are XYZ, and I kind of know what to focus on. Whereas in the longer patent application, there is a lot of bulk added for enablement and comprehensive disclosure, and sometimes it obscures a little bit the point of the invention. So that can be helpful. Can we move on to the next slide, please? So once you understand the invention, you have to describe it. And so what I do when trying to kind of structure my specification is to ask myself, how do I teach what the invention is, right? A patent application, it's a teaching document, and I think primarily, and secondarily, I would say a marketing document. So the two things I'm always trying to convey is, what is the invention and how does it work? And the more complex, the more difficult it is to do this in a way that somebody who is not the inventor or a close colleague of the inventor can follow. The audience in this case is primarily, in the first place, the patent examiner. And the second aspect is to kind of convey how great an invention it is. And that goes to, that's kind of the marketing side. That goes to explaining what the problem is, what the technical solution is, to which extent the invention is an improvement in the technical field. All of these things can be very helpful in prosecution. To explain the invention, whenever it's possible, I like to use schematics to kind of get to the basic concepts, but it really depends on what the invention is on, right? If you have a complex neural network structure with many layers and interactions in between, that can often be very well be captured in a drawing, and it's really useful in prosecution to go back to that and walk the examiner through it. Now, if your invention, really the gist of it, is in a new kind of cost function that takes a particularly structured output of the model and contrasts it with, it tries to measure how the goodness of it, so to say, then it can be very difficult to come up with an adequate drawing, and you may be relying on the math and equation in the application. In general, I would say, don't be afraid of math. Don't be afraid of putting it into the application. In many cases, so in a patent application is of course not a thesis, and not everything an inventor gives you has to be included. But in these machine learning inventions, I find it extremely beneficial to have a good bit of math in there, if they're the mathematical types, if that's their nature, because it gives you a fallback position. If you are not quite accurate, if you're describing something that's somewhat vague perhaps, and later on you come back, you try to refine some point, you can go back to these equations. There's a reason we use the language of math to describe mathematical structures. It has a certain inherent accuracy that can be beneficial. So I would say include it. Now, when it comes to efficiency in drafting an application, focus on the point of novelty, but provide enough context for full enablement. And so oftentimes, once you've identified the point of novelty, the things that are not novel can be referred to, can be simply referenced. If you're referring to a known concept, it may suffice to put that in, or maybe include something, incorporate something into the application by reference, or even better, if you have good boilerplate, that can be extremely helpful as well. Now, Jose, please add your perspective and give us maybe some insight into your prosecution experience.
Okay, yeah, next slide. Thank you, Sabine. Well, this is about claiming the invention. I think it is tied up with what Sabine was talking about, but basically you wanna cover the technical novelty in the claims. So tied it to the practical application, so it helps you with 101. And always, like as in everything, you have to look at a trade-off between the breadth, you want broad claims, and patentability. You want to be specific, especially, since Alice, we want to have technical details. So anyway, bottom line, consider the novelty of the invention and make sure it's reflected in the claims. And also, there's other secondary considerations about detectability and infringement scenarios. You don't want to have a split infringement between the guy that builds the model and another guy that uses the model. So the claims should be drafted from the point of view of either the guy that's using the application or the guy that's creating the solution. Anyway, sorry, I might be speaking a little fast. We're running a little behind, but next slide, please. So basically in prosecution, some of the things that happen in the prosecution is that anything can be a model. I mean, you put your machine learning model in the claims, maybe broadly claimed, don't talk much about the features, try to keep it broad. And the examiner just talks about some program from 1980 that is just gonna uses fudgy logic or something else. So not everything can be a model, but for examiner it is. So you need to make sure you have a good description of your machine learning models. And typically you have a good boilerplate, so you can pull that from the specification and put it in your claim. So you don't want to have to go to Wikipedia to fight with the examiner about what is a machine learning model. Other things that might come up, and with regards to 101 is like the examiner might say, oh, this can be done with pen and paper. But I say, there's no machine learning without machine. So it's about using large amounts of data and having machine uses algorithms to learn from it. Anyway, so this is a little bit the same as drafting. So the distinctions in technical details, etc. And I just want to mention from personal experience, it appears that there are fewer 101 rejections today in the area of machine learning as this compare, with from where it was 2 or 3 years ago. So the examiners know more about machine learning, know about machine learning models and artificial intelligence. And I think we've made great progress in not going to the basics and just making good conversations with the examiners. So next slide, please. So now we're going to talk a little bit about examples. And this is a real cases from real life and just talking about how we approach the claiming of the invention. And as Sabine said, the novelty can reside in many parts of the process. It can be in the training data, it can be in how you get the training, how you do the training, how you prepare the features, how you represent the data, how the algorithm, improvements on the algorithm, or how to use the model or combine models, etc. So we have some examples today that talk about the training process, the use of the model and the AI application, or preparing data for machine learning, and the use of a neural network model and training input. So next slide, please. This is a particular case about adversarial teacher-student learning for unsupervised domain adaptation. I mean, Garth at the beginning mentioned about adversarial networks in that example that he provided. And this refers to claiming the training process. Next slide, please. And basically, the leverage here, we have a teacher model and a student model, and we leverage what we learn with one machine learning program in another one, what we call the student. In this particular case is about speech recognition. The teacher model is a speech recognition in a clean environment with good sound. And the student model is a speech recognition with a noisy environment. Of course, it's much more difficult. So what can we learn from a clean environment and bring down to the student model? Next slide, please. And what we do is, we have our teacher model, we have our student model, they have, their training data, and we have these adversarial conditions. And basically, the adversarial conditions refers to, basically, you want to have as good quality recognizing speech while keeping, the loss from one model to the other to a minimum, right? And next slide. So I'm not gonna get a lot into the details, but you can see there's a left side where we have the teacher model, they have the student model, and then we have adversarial conditions that work with each other. So we work the student model after we have the teacher model we're aiming for. And if we go to the slides in the next slide, sorry, the slide to the claims, this is how we claimed it. And first, we start by training a teacher model based on teacher speech data, right? Then you initialize the student models with the parameters obtained from the teacher model. So in this case, we don't start from zero. So we start leveraging what we learned from the other model. Then we train the student model with adversarial teacher-student learning based on the teacher speech data, etc. And then we go into defining a little bit more detail. What is this training with adversarial teacher-student learning? And we want to minimize a teacher-student loss that measures the divergence between the outputs between the teacher model and the student model. That is, they both recognize speech as well. Minimizing a classifier condition loss with respect to parameters of a condition classifier, and the classifier condition loss measuring errors caused by acoustic condition classification. So we want to minimize the errors of the noise introduced in the environment. And then maximizing a classifier condition loss with respect to parameters of the feature structure. Again, the feature structure using for both models. And finally, recognizing speech with the trained student model. Again, it's very important to talk about the practical use of the claims, and that help us with patentability and 101 rejections. So this case, as you can see, was very technical, focused on training, and was allowed without prosecution right off the bat. Next slide, please. Again, I apologize if I'm going a little fast, but I'm trying to focus more on the claims than trying to explain all the technology. This one is a smart communication assistant with audio interface, and this is about claiming the application. As you can see, there's a person running here. The idea is somebody that's running doesn't have a keyboard, but how do you interact with this person via voice, and how do you get information that comes that is urgent for this person to know. So it's about analyzing data and providing a verbal user interface. Next slide. And this is a little bit, it shows a diagram of receiving requests via the speech, like give me some information. And then there's different models that provide in parallel, get a summary or read the message, analyze contents, respond to communication. There's different actions that can be taken. And if we go to the next slide, this is a little bit, next slide, please. A little bit about the gist of the invention. Oh, we went one too far. Thanks, Michelle. And this is about you analyze the message, and there's a bunch of models here operating in parallel. One is a score sender. If the email comes from your boss, you might want to give it a high priority. Or if somebody's asking you for an action item, is different than some kind of marketing communication. Or if you want to get you're checking in an airline in 3 hours, so that might be, as time goes by and closer to the flight, might become important. So all these activities, possible activities, are different models that provide a ranking score. And then on box 622, we calculate the message score based on other scores. It's not an average, right? Because a very urgent message from any of the categories may make that message very important for the score. Then you determine the basis priority based on the ranking, generate the summary, and then we send a verbal summary to the user. Next slide, please. And this is, before going to the claims, this is a typical kind of boilerplate feature for machine learning model that we use, or that I use, and talk about the training data is important, the machine learning is in program, the features, etc. And the features here is what define the model and the application. It's always good to customize your model from the other ones, talking about message word, message concept, communication history. But because the machine, the algorithms are standard. So the training data it's not the focus of the novelty, but identifying features can become very handy when doing prosecution to differentiate your model from another model. Next slide, please. So let's look at the claims here. And as you will see here, there's not a lot of machine learning model. You kind of keep at a high level and broad, because in patentability is about finding the novelty and try to get broad claims. And some things you might want to put into the dependent claims. So anyway, basically you got messages. Initially you get messages from different sources. You analyze the message to determine a meaning of the message. First you do the natural language processing and try to figure out what this message is about. And then you get a score for each message based on the respective message and the meaning of the message. And as you can say, this building the score, I saw you that other slide that's with multiple scores that might come into place. But again, that's for the dependent claim. Now you select a message from the, based on the score of this message, provide the textual summary of the message, or something that can be digested easily by the user. You might have a long email, but you just want to provide something quick to tell the user that doesn't have a lot of time. Then create a speech summary, and then they send the speech summary to a speaker. So this is a lot of things going. I think this is a good claim. It looks like it's a long claim, but some of those things are very common, getting information, analyzing information. So overall, this is a good claim because it doesn't get a lot into the nitty gritty, but it gives a very good high broad analysis of this assisting with the speech. Next slide, please. Okay. This one I'm going to go a little bit quick, again, because we're running a little bit low on time. This is preparing the data for machine learning. Next slide, please. One of the things with machine learning is image recognition in particularly is that it requires a lot of data points. Visual recognition requires hundreds, if not thousands of images. So typically when you're doing classification, like Google search images, identifying people, you have a lot of images. But then you can have a problem when you have only a few images, maybe one image over a handful of one person. So that person is going to be difficult to be represented. So next slide. So what we do is we promote that person. Here we talk about a loss function here. This is the math. How do we get that loss function that the machine learning algorithm uses to promote this underrepresented class? And anyway, next slide, please. And as you can see on the top left here on chart 602, this is the data points, and they're identified by colors. As you can see, the data is very well separated. On the other hand, on the right, we have data, also the similar data separated in space, but there's an underrepresented class, that lonely kind of single dot on 606. If we do a machine learning classifier that, basically what the classifier does is divide your space. This is a two-dimensional space, but usually we're talking with 20, 100 dimensions, but it divides the space into each class. So when you get a data point in that, look what it falls in the space and you classify. But if you don't promote that underrepresented term, you don't get a space defined there. However, on the chart on the right on 610, we can see how by promoting this underrepresented class, we created a space to be able to identify that person. Next slide, please. And it gets to the training, to the claiming. Basically, you identify a training set, you identify the base set and the novel set. You have two sets. And one is first you just do the base set just without promotion. And then you train the first classifier with the base set and without the novel set. Then you train the second classifier using the training set with promotion of the novel set. And and then you talk about minimizing a loss function with the prices of first term, a second term, and describe a little bit of the math. But we're trying, one of the problems with math is that 101, the Supreme Court has said, and I wrote an article about it, that math is not patentable, which is absurd because math can do a lot of things. But we try to hide math or describe in language what is happening and not just the equations putting directly in the claim. So, and anyway, once we get that, we classify an item with the trained second classifier, practical utility. This was again a good claim, is detailed but not too detailed, and it was allowed without prosecution because it had good novelty. So now there's one more case that Sabine is gonna describe for us. Sabine, can you tell us about it?
Yes, one last example to illustrate. Next slide, please. illustrate a case where you want to claim where the invention resides kind of in the model, in the machine learning model that's being trained to accomplish something. So the task here is the one of program synthesis, where a computer writes an interpretable program, a program in some kind of domain-specific language, based on a characterization of the inputs and outputs of that program. So as an example, think of the language of the kind of programming, domain-specific language of string transformations, where the input may be, for example, a name, as you see in the table on the left there, William Henry Charles, and the output is the name rewritten with last name, comma, first initial. So input and output pairs are in this case the input to the machine learning model, and what the model generates, which you see on the very right, is a program in the form of a representative, in this case as a program tree, which is kind of a recursive substitution of instructions, if you will. So you can imagine in this case of string transformations, you start with kind of your node that you replace with the string, first element, comma, second element, and then the first element you substitute with kind of the last word of the input that begins with a capital letter, and then the second element is the comma, the third element would be the first letter extracted from the first word, something like this. So that's kind of the program that's being learned, and in use of the already trained machine learning model, you get the input-output examples on the left. They're encoded in some manner, and then a neural network is used multiple times to iteratively expand this program tree, and in each iteration compute a probability distribution over all possible expansions. So this avoids the need to kind of use all permutations of the instructions you have available in the language. It's not a brute force method, but it's informed by the input-output examples as conditioned onto this neural network. And so the training input to this case would be a set of programs with corresponding sets of input-output examples characterizing the program. So the training is really programming a model, a second program, to generate the third program, the learned program. Now, how do we claim this? Can we go to the next slide? So this is a case where we're trying, this is a claim where we're trying to capture not the training method, you could do that as well, but it's trying to capture actually the function, the operation of the already trained model. Nonetheless, we want to reference what the training data is, and you see this bold-faced italicized phrase here. We're talking about a program generation model in an input encoder in a neural network having been trained on a plurality of programs within the language and a plurality of corresponding training sets of input-output examples. And after this setup of what the training data is, we're going into the individual steps. You're providing it. So in the inference phase, once the program has been trained and we're trying to generate a target program, we're providing a test of input-output examples for the target program, conditioning it, encoding those examples, conditioning the program generation model on the encoded set of input-output examples. And then the last element here is really the one that tries to capture some key features, and you could go different scope here of how this works. So it's using the neural network to generate the program tree that represents the target program by iteratively expanding a partial program tree based on a computed probability distribution for a set of valid expansions. And the way the computed probability distribution is computed is not included here at the independent claim level, but if we can go to the next slide, it was included in a dependent claim. And just to pick out kind of some of the elements here. So the neural network in this case is what the inventors called the reverse recursive neural network. And you can see it's getting quite complicated, computing a global leaf representation for the nodes, by retrieving distributor representation, and so on and so forth. I actually don't want to go through all of it, but it's a very detailed description of what the model does. And this claim, actually, the dependent claim got allowed very early on in prosecution, but it wasn't necessary in the end to get to put all of that in the independent claim. So I guess the lesson is put something of essence into the claim. Don't leave out, the gist of it, but you can stagger it in different claims, and you may want to consider even claims of different scope, between different independent claims. And I think we're out of time, but we've gotten through the bulk of it.
So just for
to you.
Yeah, so the slides are going to be available online, and they should be sent to you. I think just want to thank Jose and Sabine for the presentation. This is a really complex topic to discuss, and the nuances of claiming artificial AI-related inventions could probably take up an hour in itself. So we hope that this broad overview has been of use and of guidance. And if you do have any questions, you'll see that our email addresses are provided in the next slide deck, in the question section down below. There we go. And so feel free to reach out to us, and we will gladly cover any of these aspects in more detail, or answer any other questions you have. So thanks once again for joining us. And if you are interested in IP, do look at the other episodes that we have coming up in our destination IP presentations, and those that have already taken place, the recordings are available online. So once again, thank you for taking your time to attend. Bye-bye.
Thank you. Bye.